So the motional EMF drives the eddy currents, and we've got our area declining as this guy leaves the region of B field. Here's the region of B field. So this area in here is the region of B field, and it's leaving this boundary. And as it leaves the boundary, the area of that plate is going to get smaller, making the flux go down. So we would now have area times our B field times cosine of theta, but our cosine of theta is equal to 1, so theta equals 0. Cosine theta equals 1. So we end up saying that the A decreases. So A initially is greater than A finally. And therefore delta phi, which generates our EMF, is equal to phi final minus phi initial. And that really comes down to, you factor out this B cosine theta because that doesn't change. So we factor that out, and we're left with A final minus A initial. A final is less than A initial, so our delta phi ends up being negative, okay? So we end up with a negative in this situation, okay? A negative number. Whatever that number is, that's our phi, and that's what we're gonna go through. Excuse me, I might have to sneeze. Okay, that's the phi that we go through. Hold on. Okay. So that gives us our EMF. All right, so our EMF is minus delta phi. Now our n is equal to 1 here. We've got one plate. So actually the n's, crazy little loops develop all over the place, but just think of it as one n. So what is the EMF? Okay, so let's figure out what direction this is leading. Our B field is going up. The Lenz's law forces our current loops to go around in a loop. So let's just think of the whole thing as being one large loop. And which direction is the current flowing? In other words, what type of EMF are we driving to get the current to flow this way? So let's change our picture. Here's our B field area. Here's our escaping plate. And the B field, let's call the B field out of the page, just so I do it differently from my notes. So we've got a B field that's out of the page. And of course, this is a plate, all right? So this is a solid thing, but we're gonna look at just the edges, okay? We're just gonna figure out the edges, and then we can say, oh, well, our eddy currents throughout the plate are gonna go in a certain direction. Okay, so we've got our velocity going in this direction. We've got our B field going into the page. It's an external B field. Okay, And we're going to apply this situation to this. So what is our force? So on one side, we're leaving okay. So this is where it gets tricky. We're leaving this situation. So we've got our B field. Let me erase that. We've got our B field going out of the page straight at us. Okay? It's decreasing. The flux is decreasing. So in order to make the flux more, to make that B field maintain its direction, current has to develop on this plate so that the B field is restored, because we're losing flux. So we're going to try and increase the B field in a toward us direction. So how do we increase the B field in a toward us direction? Put your fingers on the inside of the plate and point them at you, okay? Because it wants to make the B field maintain its strength. So you put it towards you, and where does your thumb point? Your thumb points in this direction. If you had your palm facing you and your fingers on the inside of the plate. Now you put your fingers on the inside of the plate, like move your arm up to the top of the page, put your fingers on the inside of the plate for the top part, and that's where the current will be going. And you can do the same for each of the sides, and you'll notice that your current is going in this direction. So that's a counterclockwise current. So all, if we were to let's draw our escaping plate, escaping the B field, going in a direction V. All the little eddy currents that are going to develop are going to develop in a clockwise fashion. So a bunch of eddy currents are going to develop in that clockwise fashion. And it wants to slow down this item from leaving. It takes energy out of the system, and therefore tends to make our velocity go down. All right? Because friction is stealing energy through the eddy currents. The use of eddy currents. Okay, we could do the same thing on the other side as it's entering. You might want to look at that in both situations. So figure out which way the force is going for both situations, but let's figure out the direction for the force in our situation. So we definitely have a force, and that is our F equals I L cross B. Okay, so I don't know if you want to think of L as having the vector or the I as having the vector. It doesn't matter. Either way, it's going in a certain direction, and we're going to cross B with it. So our current is going in the counterclockwise direction. We put our fingers along the current. We curl them toward the B field, which would basically put your fingers going up the page on this side. So we're going to do this side. Our fingers going up the page. We're going to bend your fingers toward your face, and your thumb points in the direction of the force. So that force would be going to the right. So whatever it is, I, L, B, and it would be in the, if we say this is I hat and this is J hat, then it would be ILB in the I hat direction, positive. That would be our force. All right, and you can do the same thing for the other side, and you'll notice that your force is again in the ILB direction. So, okay, I think that does it for that. Let's move on to the next thing. Electric motors. So they do the opposite of what we were talking about earlier when we were generating current. And because the electric motor is so let's do just do a little explanatory thing here. So what do we have? We have two different things, but they're the same thing, just one's running forward and one's running reverse. So we have electric generator, and we have electric motor. Okay, and it's the same electric generator, electric motor that we showed earlier with our we've got something and it's spinning inside a constant electric field, constant magnetic field. So that's happening, and it's spinning around an axis right down the middle. All right, that's its spinning axis, and of course it's got a length and a width and all that, whatever. We already talked about all that. So when we're doing a generator, we're doing the generator such that the we are taking kinetic energy. So we've got kinetic energy, and we're transferring that kinetic energy into electrical energy. Okay, and it's a current, essentially. We're developing an EMF and a current. We've got a current, and then we can then take that and assign it to charge storage. In a battery or a capacitor or something like that. So we're taking kinetic energy and we're turning it into electrical energy. Over here, we've got the same device, right? Only now we're driving the spinning device with current. So we're taking our electric energy from a battery or whatever, and we're running that current through the loop, and then that current driving through the loop is going to give us our kinetic energy. So it's the same object, it's just running forwards in one side and running backwards in the other. But, however, we have back EMF with an electric motor. All right, and back EMF happens when the motor is spinning. The loops are spinning, but they're also generating their own EMF because they're spinning as well. So this is called a secondary EMF. And it only happens on the electric motor side, right? So you don't get a back EMF unless you're using your generator as a motor. Secondary EMF. Okay. Let's move on. Let's move on to transformers. So transformers is... I've been listening to that commercial since the 80s. So that's why I go, Transformers. Okay. So, Transformers. Cheap. That's the first thing that comes to mind for me. They're inexpensive. People don't like the word cheap, but they're inexpensive. They're an inexpensive way to raise and lower voltages. Okay, however, they only work for alternating current. So, true, only work for changing voltages. Changing voltages means alternating current. Okay, we're changing the voltage. That means our current, our voltages are changing, and our current then is changing. Okay, so one's current. That was dumb. We've got voltage and we've got current. So the current is, of course, not equal to the voltage, but it's proportional to the voltage, right? Because V equals IR. So at every point, the current and the voltage are in sync with each other and oscillating. So we have a changing voltage means AC current. All right, so it only works in this situation. And why do we do that? Because power lost is equal to I squared R. Okay, so here's where it comes in. The transformer equation. Let's move up a little bit. So here's where it comes in. We've got our transformer equation. So we could say our our voltage in over our voltage out is equal to our N in over our N out. All right. That's great. That's really good. But now, what does that mean for our current? So let's see. Do I have that one written? Yeah. Good. So if we've got V in on top and V out on the bottom, our current out and our current in, and we derived this in class, but I'm going to keep it like this. The current is reversed, which means that whatever you could be supplying V in with, times our I in, that equals our I out versus V out. All right? Keep in mind this equation, okay? Because we're going to come back to this in a second. Let's say that our V in, we just generated the energy, and we've got V in and I in, and what we really want to do is reduce our power lost. How do we reduce that power lost? Well, we can't change the resistance in the transmission wires. That's going to stay constant. So our resistance is going to not change. But we can change the current. So we can do a step up. So our V in is less than, and we can make it a lot less than, V out. All right. So then that means that I in is a lot greater than I out. Right? This equation insists on this. So our I out is the one that we're going to have going across, because we have generated the electricity with our generator. We've got electricity going through the wires to a transformer. Let's draw a good transformer. Make it a nice, good transformer. Okay, and then we've got our wires going around this thing right here, and then they go back. And then on the other side, we've got, and I'm not gonna, what do we want? We want V in less than V out. That means the number of in coils is a lot less than the number of out coils. So we'll have a whole bunch of out coils, and then we'll have a voltage difference across that going out. Okay, so good. I don't like the way I've drawn that. We've got a generator. Come on. Got a generator, and this connects there, and this connects there. Okay, so we've generated this current. We've run it through a transformer. Here's our transformer. And we've got some high voltage V out. And our current is nice and small. I out is small. That takes us to the resistance in the transmission wires. We're going to square that very small current. We've got the resistance multiplied by it, and we're going to end up with a lower power loss than if we had not done that. Okay? So we needed to make our current small. That gives us a small power loss. That's it for the best example of why we use transformers. But of course, you can't live your everyday life like that with this high voltage, right? People would be dying left and right. So we don't need that, but we could then do a step down transformer, or in other words, flip the transformer around. We flip this guy around, and we end up with a step down transformer. So N in is bigger than N out. Bigger than, greater than, and out, and that is our step down. So a step up is N in less than N out. And yeah, that pretty much nails down transformers. So we can go back to E&M waves a little bit. Everything there on page 58, those E&M waves, that's, I can't do any better than that. So I'm not going to try. Let's move on down to a larger frequency has more information or bandwidth. So we can look at our frequency scale. So we go all the way from, I don't remember what it was, but I think it's around 10 to the 24 hertz on one end, and let's do 10 to the no hertz. What is that? 1. Okay. So we're going all the way down to 1 hertz on one side and 10 to the 24 on the other, and right in here around 10 to the 14 and a half, 10 to the 15, right in that range is visible. And that's roughly 10 to the 14 hertz. So that frequency gives us more bandwidth. So down in these ranges where we've got FM radio, AM, FM, microwaves, which have nothing to do with the 10 to the minus 6, it's just called microwaves. We've got centimeter waves and meter waves and all those things down there. All this is infrared, but all this region down here in the infrared does not hold as much information as the visible light scale, right? As soon as you jump a factor of 10, every time you jump a factor of 10, you're increasing your bandwidth by a factor of 10, and you're able to do transfer a lot more information, right, over a higher bandwidth. That's why optical cables, fiber optics, I don't know why, it seems like I'm French because I always want to do RE. Fiber optics, fiber optics, definitely have much more bandwidth. Than radio waves. Come on, waves. So, true. To observe an object, we need to use the correct lambda for the size of the object. There's also resonances, right? So, antennas work with resonances. And usually they're a quarter wavelength antenna. So the antenna on your car is roughly 1/4 of the wavelength that it will be accepting. And your antenna is for FM on your car, by the way, and then inside your receiver, inside that little box, is a coil set up with a whole bunch of loops. It's a solenoid around an iron core, and you've got one wire going in and one wire coming out, and that's how your B field is caught due to the AM waves. So that's inside your receiver, and it catches the B field. Now, the same thing happens to be when you have a large bridge that's iron, right? Iron and concrete, in your large bridge, that iron and concrete are going to resonate with the length of these wavelengths, because they're going to be on the order of 10 to the 3 meters or more or less. So a 100-foot bridge is going to resonate with that and block your signal. That's why you drive underneath the bridge and you don't get signal. If you're trying to listen to, who's one of those talk show radio host guys? I don't want to date myself, but there was, I don't know, back in the day, let's see, maybe I do want to date myself. This one dude got murdered in Denver. You could look that up. He was a radio talk show host. Somebody didn't like him. He was either too liberal or not liberal enough. I don't know. Or too conservative is another way of saying that. Okay. Material boundaries or interferences are places where the value of the speed of light changes. So I'm going to use the glass example. So C for air is roughly the same as the C for a vacuum. But inside glass, there's an N for glass, and then there's an N for air. And that changes, okay? And that means that we've got some line coming in, and it's going to be straight going in and straight going out. The only difference is in between, inside the glass, it's going to have a different direction that it points because of the N, right? So what is it that we measure? We measure this theta in, and then we've got some, we'll do a blue theta. That's our theta 2. And then we can say, if we say that this is N2 and this is N1, then it's not hard to say, oh God, it might be harder than you think. It's easy to say this. Okay? All that means is the speed of light in glass is less than the speed of light in air. Okay, so that leads us to transmitted waves and reflected waves, and what really is happening. So at that boundary, we do have a reflected wave coming back, and we have, so this is our reflected intensity, this is our incoming intensity, and then transmitted in is our transmitted. Okay, so some will be reflected, some will go in, some will continue on. And that's just the nature of the world. So we have a reflected wave, we have a transmitted wave, and a little bit gets absorbed by the material, but not very much. In fact, yeah, more than you would think, because it happens again at the next boundary over on this side. It happens again, so we transmit our transmission, our second transmission, T2, is going to even be less because there's stuff bouncing around inside the inside our glass. Okay, so let's talk about intensity. Intensity instead of, okay, it's easier to work with intensity instead of energy. And you can get the energy. I think we did that earlier, where you can go back and forth between intensity and energy, but we're going to just look at straight up intensity. And we're looking at the peak intensity. All right. But just so you know, 2 times the average intensity is equal to the peak intensity. All right. So all these equations I have are for the peak intensity, and I'm going to just do it like this. Our first one is 2I average, which I already said. The second one is C over mu naught times our B max squared. The third is C times epsilon naught times our energy max squared. Not energy max. Our E field maximum. So we've got B field here, we've got E field there. And then if we were to multiply the E field with a dot product and the B field, and we divide that by mu naught, that also. So all of these things equal our maximum peak intensity. So optics and light, these are we're on the home stretch, getting into optics and light. I already kind of did Snell's law for us, but I didn't do the law of reflection. And that law of reflection says that the theta incoming is equal to the theta reflected. Okay? Easy. That's the law of reflection. All right. Does it pertain to meditation and reflection? Probably. Okay. The law of refraction is just what we call Snell's law. And that means that the n of a material is equal to the speed of light divided by the speed of light in that material. Okay? So this is always compared to vacuum. All right. We went through and we figured out n of glass before because we knew the C for air. We used essentially 1 because it's essentially 1. And we said, okay, what is our n for the material? I don't like that n. It's all, when we're doing this kind of stuff, it's always this size n. Lowercase n. N for the glass, I don't know. Some people came up with 2.1 and it ranged all the way down to 1.2, I think. I think it's a little closer to, is it? No. That one's a little high. That one's high. It's probably a little bit closer down into this range, the 1.5 to 1.2 range. But yeah, because diamonds are 2.1. So And the glass is definitely different than diamond. Anyway, we talked about Snell's law, so let's talk about total internal reflection. And this is where fiber optic cables come in. Fiber optics, total internal reflection. So if you get a low enough angle, your other angle, the transmitted angle, goes to 0. Or, I'm sorry, goes to 90 degrees. Can't go to 0, it goes to 90 degrees. So, all right, so that's 90 degrees. This is theta critical. And as soon as that happens, then everything either goes along the length of the object or reflects back, right? Because there will be the reflected theta I. This is our theta I over here. Theta I is equal to theta R. Theta I happens to equal theta C at this point because our transmitted is going along the surface, and everything basically goes into our reflected. Okay, so, and then that's, of course, we have N1 up here and N2 down there. That means that theta critical is equal to the arc sine of N2 over N1, and because the sine of 0, the sine of 90 degrees is 1. And that's the news. Okay, so corner reflectors. Hopefully you guys remember that we've put a corner reflector on the moon, and essentially what happens with a corner reflector, let me draw Cubert here. We'll have some incoming, these are glass mirrors, so some incoming wave is going to go there, it's going to hit here, it's going to hit here, and then it's going to come back out in the exact same direction as it came in. All right, it's a pretty cool reflector situation, and it works really well. And all you have to do is make sure that they're all 90 degrees to each other, these mirrors. And you can make them. They make them on the reflectors on your bicycle, or corner reflectors. So it's nice. So on the moon and on your bicycle. Everybody has a bicycle, and I know there's a Y in there somewhere. Okay. Good. Dispersion. So when somebody talks about dispersion, anytime you hear dispersion, you should think rainbow. Okay, and how does the rainbow come about? Well, that's simply because we'll draw the Pink Floyd deal. It's simply because the N of the material, oh, I did it again. Our N of the material is such that different frequencies are changes in N, different frequencies have slightly different, let's put a slightly there, N for the material. So there's a material dependence on frequency. And that material dependence causes a stream of light that has white light hitting here. Each of those bends are going to be different. And it's going to happen twice. So the thing that you get out of it is our rainbow. Which ones curve more? I think the higher frequencies. I don't know. Being colorblind does not help me in this way. But I think we've got the reds down here and the blue violets up there, but I could have this thing totally backwards. I just know that there's definite difference, and it separates them out into their different colors. So yeah. I should be like, okay, which one's gonna bend more, this one or that one? I don't know. You can figure it out given their N dependencies, right? So once you're given N for red, it will either be bigger than N for blue or violet. It'll be bigger or smaller than that. So this will be either greater than or less than 1, right? And that's how you figure out the angles, right? Because you come here and you notice that this angle here and this angle here, one's going in, one's coming out, and you're going to use Snell's law. And then you're going to know for Snell's law, this one might be a bigger angle than this one, or vice versa, right? So you go through, you do the math and you figure it out. So it's easy. Snell's law, easy. Everybody can do it. So that's that. Let's move to page 62, image formation. So we have power, which means diopters. So I call it a lowercase p. And that p is equal to 1 over the focal length. And we're not dealing with the big power, quote unquote, energy divided by time. This is measured in diopters. Okay, which diopters is just a big capital D. And D is equal to 1D is equal to 1 over 1 meter. All right, so we do thin lenses. Why do we do thin lenses? We do them to keep down aberrations. So we have thin lenses. Minimize distortion. They minimize dispersion. I don't want that, I want this. And the last one is aberrations. And it's not two B's, it's two R's. I always get that at the end. Okay, so thin lenses. You want to deal correctly with thin lenses for this reason. And that's why we use the thinnest lens we can possibly use so that we minimize this effect, dispersion. We're minimizing aberrations because of the local densities in the material could be different. Like the density in this region could be different than the density in the rest of it. And then any light that goes through there gets dispersed weirdly. And that causes weird things to happen. So you want to minimize that. So you keep the lens thin, right? So that does your aberrations and distortions, right? So that's what we're talking about. We want to minimize differences in the material of the lens. Okay, so then what I would recommend is that you practice some ray tracing. I think I'm gonna just say ray trace in the lab from now on. I'm not even gonna tell you how to do it or describe it in any way. I'm just gonna go trace a ray from here to here because that's pretty much the right way to go. So practice some ray traces. I gave you some examples, diverging lenses, converging lenses, flat mirrors, you know what that is, concave mirrors and convex mirrors. And then the last thing is our thin lens equations. So we've got thin lens equations. So let's look at those. Now don't forget, and this is one of the questions I get kind of often. It's I got this answer, but it's not right. And why? Well, probably because you have forgotten the minus sign. And when you're dealing with the lens, you draw your lens. Some ray of light is going to come in here and do this. Some ray of light is going to come in here and do this. This is your focal length, but you have to decide which side of this line, this is 0, which side is positive and which side is negative, okay? And that's where this negative sign comes in. And this is your magnification. M, okay? M is the magnification. So that's where the negative sign comes in. So you have, to get it right, sometimes you got to say, oh, which side am I on and which side did I decide was going to be positive? And then I have a positive or a negative, depending. Of course, F is our focal length, right? And we have an image. We have an image distance. This could be our image right here. And then we have an observer distance. Okay, a DO somewhere over here on this side. So that's DI and DO. And then, of course, you have to figure out which one's positive, which one's negative. And when you do, great. And then the last thing, if you do have a radius of curvature for some object, maybe it's a concave lens or what have you, this is a radius from a certain point. Your radius is 2 times your frequency, your focal point length. So your focal point would be halfway. That would be the focal point length. When this is R. That is it, guys. I'm going to post this. Good luck on your final, and I'll see you when we take the